I get the feeling that there's a theme to this session, and that theme is Oswald I. But, yeah, quite. I've also, due to the inadequacy of the networking here, and the fact that everything got rearranged like 4 times in the last 2 days, I've had to rewrite the talk. So it's almost, but not quite, totally unlike what was written in the blurb. I want to have a bit of a rant. But only a little bit of a rant. So here we are, Python. We like Python. It's dynamically typed or not, depending on how you use it. And it's sort of quite popular in data science amongst those people who don't use R and Lisp and languages like that. Us sysadmins have probably been using it since about 1991. So none of this mucking about with 2008 rubbish. Oh, no heckling net. Okay. And a few people use this web. I have no idea about the web. So have you noticed how Python development is now being driven by IDEs and not by language define and other sorts of usage? The whole 484 thing, or whatever its number is, it's all about MyPy. MyPy should have been a Python interpreter. And that's, well, never mind. And that's a different rant. The main thing is that Python is slow. Very slow. Oh, yes. Yes.
No.
Proof it.
No.
No, you see.
It is fast. I work and I am a much faster developer. I get my guys...
Yes, you see. Yeah, it may be fast to get the code working, Pandas and all that sort of stuff, but then when you want to crunch the numbers, you're no way going to do it in Pandas.
Oh, no.
Because you can't...
Optimization for speed is just an optimization, okay?
Yeah.
Some of the time, a lot of the time, you get to the end and Python's fine.
For one-off, if you're doing finance stuff, no, once you get to 4, forget it.
Sorry, it's a fallacy. This is Python.
See this book? Don't buy it. Just get the free one. Anyway, we hate the GIL. I've hated the GIL for many, many years. Why? Because parallelism. If you have a GIL, you don't have parallelism. Camel have proved this. Oh, and so has Python. And so what do you end up doing? And you read Ian's book. It tells you all about things like Numba, Cython, NumPy, and all that sort of stuff. And NumPy's really old hat. You know, it's idea of arrays and things. Yeah, it's sort of good, just wrong. Cython, good thing. Well, Pyrex was a good thing because that's where the idea came from, and Cython is then the production version of it. And so that's, we always have to have the hats off to Pyrex when you mention Cython. So that's good stuff. But it is actually just C in the end of the day. Why do you want to write C in Python? This is not a rhetorical question. Why do you want to write C in Python? For speed. So why not just write C in the first place? Yes, very good. Excellent. We like that. Also, because C is not an applications programming language. It's a systems programming language for writing operating systems. So are we writing applications in a language that was designed to write Unix? Not anything else, just Unix. Well, that's the end of that bit of rant. What we really want is Fortran, because this is the one true language for writing mathematical code in. And hats off to anybody who knows the difference between Fortran and Fortran.
Which generation of Fortran it is? That's Fortran 4, I think, was the last one with capitals.
Actually, Fortran 77, but
okay, right.
yeah. But you're quite right in that the Fortran, the big uppercase one is sort of the original, 1, 2, 3, 4, 77 and so on. And then in 1995, they formally changed the name to Fortran with lowercase letters, for some reason to do with words and things. But who the heck wants to write in Fortran? Well, me, I do a bit, but not a lot. And then you get to Numba. Take your Python, run it through, LLVM, stuff, which is not bad stuff, and you end up supposedly with fast code. And no, but we'll see that in a moment. The question here really, though, is if you're writing Python, are you writing a native code language? No, because everybody thinks of Python as a dynamic language. It's typed or not typed, but it's dynamic. It's not a static native code system. Does our Python have? Well, apparently yes, because the PyPy people say it does. But there are some subtle differences between Python and our Python. When you just look at the page, you might not get those. But in the end, it's not a native code language. It's a language designed to represent code for a dynamic virtual machine. Then we get to NumPy, and then the whole SciPy, Pandas, scikit-learn. I'm sure there's another package this week. Underneath, it's C. Yeah? It's basically a C array. And then you just chuck functions at it. People keep showing me this code that's supposedly using NumPy, and they're indexing into NumPy arrays. I'm thinking, which planet did these people learn NumPy on? NumPy is all about being an opaque array type. You create an array in the box, you throw functions at the box, and you get results out. Any other way of using NumPy is just, well, wrong. But underneath, it is just C. And is C good enough for what we're doing these days? And I think the answer is fairly much not yes. Why? Yeah, same problem at the end of the day, is that C is a language for creating operating systems. Operating systems don't really care, or didn't really care that much about parallelism, certainly not in 1969 and 1970. And now what have we got? Well, your phone, well, assuming you've got a smartphone, which I suspect 99.99% of the people in the room have got, has probably got more computing power than a Cray 1. And that's just a natural consequence of time and Moore's law, which sadly has failed to flatten out yet. So you can pretty much imagine we're going to be in real trouble. And so are NVIDIA, because NVIDIA's days are numbered, because Intel have decided they're going to put GPUs on the die, because that's the only thing they can do with all those transistors. So your chips are going to come with GPUs. And if your programming language can't cope with GPUs, you've had it in the performance computing stakes. And that's going to be the big lesson for NumPy. If they can't deal with GPUs integrally, not any of this PyOpenCL or PyCUDA stuff, but integral into NumPy without the GPUs, you've had it in the future. General purpose graphics processing unit. Supposedly a graphics processor, but it was originally specialist hardware, but it was very soon realized that it was also a damn good array processor. underneath because all of the graphics engine stuff was array processing. And so they brought that array processor up onto the bus, usually PCIX or something like that at the moment. And so you can then, if you've got a decent driver in your operating system, actually download kernels onto the GPU as compute kernel. And that will allow you a 256 wide register usually floats, not doubles, for speed. And as we know, floats are completely inaccurate. So they're fine for graphics processing, but if you're going to do financial processing, you will not be doing GPUs. You will be using software floating point numbers. But that's a different argument, different rant. So just as signposts to where things are going, anybody using CUDA is doing it wrong. 2 reasons. 1, NVIDIA. Reason 2, NVIDIA. And nowadays, as of earlier this year, anybody using OpenCL is probably looking backwards rather than forwards. And we now have Vulkan. Except that they can't spell. But then again. I just thought I'd throw in a few other signposts to parallelism as we're going along the way. I'm going to be emphasizing a little bit here data parallelism, arrays, hence the NumPy link. We'll come in a minute. But there are other models of parallelism, actors, CSP, as in communicating sequential processes, data flow, data parallelism. All 1960s and 1970s technologies that got forgotten for a couple of decades and finally making their way into the mainstream again. But anyway, parallel processing in general. A lot of people may be using threads and thread pools. Was it something concurrent in Python 3.4 came along and did good things with subprocess and all that sort of stuff. What about C? Well, if you use pthreads, you're doing it the hard way, but that's all there is in C. C++, they sort of managed in C++ 11 to get some decent concurrency stuff in there, like asynchronous function call and things like that. That's good stuff. Java's been faffing around with parallelism since about 1995 and getting it wrong. But you know, eventually with systems like Akka and Quasar, they're getting it right. I don't know if anybody uses Hadoop anymore, given Apache Spark, but you know, we'll leave it. And GPARS is, of course, the greatest system on the planet, and you just have to go and look at the list of authors to understand why. And there's languages like D, which have taken C++ and 10 years later have got it right in many, many ways. And still got a few things wrong. But what have we got on the other side? Partitioned global address space. That gives the game away. Partitioned, so it's not unitary. Global, across the entire network. Address space, i.e. one program to rule them all. And there were lots of, this is a DARPA program that started 2004, if I recollect correctly. And they pumped in millions of dollars saying, what is the best way of getting productive programming of high-performance computing? And with high-performance computing, what we mean here is not a Cray 1. That was sort of 1960s. What we mean is sort of petaflop computing. High-performance computing is defined by the fact that it requires a government or a huge global corporation to be able to afford one, because they usually come in at $200 or $300 million a piece. So we're not going to get 3 or 4 in the room next door. They're appallingly difficult to program if you're using C or C++. And that was the whole point. Lots of people joined in the HPCS program, and then they got filtered down to 3. There was Fortress, Chapel, and X10. Fortress decided to resign their position. Lots of technical reasons why that was a problem. But effectively what they proved was that JVM is going nowhere when it comes to high-performance computing and massive systems. It had to be native code or nothing at all. And so Chapel and X10 are around, and I happened to have more to do with Chapel than X10. So I'm going to do a few thoughts on Chapel here rather than X10. But there are others around there as well as these two. And I've noted down the bottom here, I'm not sure people at the back can actually see the bottom of this screen, it's way too low. But it says things like Pony, NIM, and languages like that. Pony is an actor's language, doing things right. NIM is a Python-like language. It's taken that R-Python approach and saying, can we take the Python syntax and actually have a real native code language, not a pretend one? So there's a good message there. You might want to have a look at NIM if you're interested in all this sort of stuff. So where does Python fit into all this? Because I actually like Python, just not for computing. Rendering data, you know, visualization. This is what matplotlib was invented for. And okay, R has a few competitors in there. But fundamentally, Python has a monopoly on that aspect of taking data and rendering it in nice ways. And that's cool. It's just that it can't generate the results that you can then render. So it definitely doesn't fit for doing the computation. But remember microservices? I don't know if people have got into this sort of really cool way of doing things. But basically it's the actor model from 1960. It's just been rebadged. And because it's been rebadged, it's cool and new. And therefore the hipsters will allow it onto their machines. So we like microservices. What is microservices? Well, it's processes communicating over a network. And if anyone mentions HTTP, they can leave. Microservices is not HTTP bound. Microservices is about having processes communicating over a network. CSP, actors, all of those nice ideas of how to model parallelism and concurrency are coming back into vogue. And sometimes you can have those processes on the same computer, particularly, you know, if your workstation has twin Xeons or something like that, and you've actually got 8 real cores. Anyone who mentions hyperthreads will be ejected. Because hyperthreads are sort of all very well if you're doing I/O. They really aren't very good if you're doing computing. And so if your computer, like this one, tells me I've got 4 cores, it lies because it's an i7. M. i7s, 4 cores. 7M, 2 cores. And hyperthreads. Ugh, we hate it. If you think about it, communicating processes is the only way of doing parallelism in Python because of the GIL. And so we're all already fully aware of how to do parallelism in the right way, the microservices way, by having multiple processes and having them communicate with each other. The thing is, can we take the microservices model of saying, well, your microservice can be in any language you like, because the communication is what is important. Do they use the same protocols to talk to each other? If the answer is yes, we are approaching nirvana, because you can put the compute bit onto the compute engine in a compute language and ship the results over the protocol to the Python engine doing all the lovely visualization and rendering and the things that people want to do with it that Python is very, very good at. And so here's a few we could think about. Well, I think we've immediately got to get rid of that one. Is it showing? Not really. So I'll do it a lot. Do we want to do it in C++? One or two people are saying yes. I can. The only one I will accept, however, is C++ 17. If you're not using C++ 17 and you're doing parallelism, you're doing it wrong. Rust? Okay. Well, given the timing, let me just have a quick look at Chapel. I was going to do Deanne, but yeah, okay. No. Oh, that's the advert. Sorry, I've gone too far. Do you remember the ISO 8601? If you're not using 8601, you're doing it wrong. Anyway, back to a quick peek at Chapel. Let's hope that... yes, we've still got some stuff. Python. Change glasses, otherwise can't see screen. Okay, so we've got quite a lot of... Sorry, code of conduct just came into my head at that point. Sorry. Damn. Oh dear, oh dear, oh dear. Sorry about that. Okay, so we've got quite a few things. Let me just do the sequential for the moment, because I've only got a couple of minutes left. Pi, sequential. Does anyone use power in? No. Okay, so we'll just use range, multiply. And so this is a sort of backdrop of proving that Python is really slow. So on this machine, it's taken 5.6 seconds to do something. So if we go down here, and we have, what did I call it? I have to do an ls, sorry. So what we want is sequential reduce. Success! 8.6 seconds. 5.6 seconds. Brilliant! Python is doing 100 times fewer iterations. So this has done 100 times more iterations. Actually, Python. Does anybody like the reduce function in Python? Well, the rest of you are wrong. Reduce is cool, and it was completely wrong that it was excised from the language. I told you it was going to be a rant, didn't I? So if you do reduce, multiply, shouldn't take two. It's not a bad thing, reduce. Everybody in the HPC world understands reduce, they use reduce. It's critically important to parallel computing. And therefore, by demoting reduce from the language into the library, Python has flagged formally that it doesn't care about parallelism. Okay? This is a sort of mindset thing, an expectation thing, a social thing. But it is nonetheless there. It's a flag that's saying we don't care about parallelism. But it doesn't matter, because we've got microservices architectures. Put the compute in the compute area. So what's the big backdrop to this? Okay, so I've got a sequential reduce and I've got a parallel reduce. And I'm going to do it not batched. Okay. Now, what's the real win here? So if I just have a look at the Chapel code that has done this, it would help if I could type quicker. Okay, so this is parallel code. that ran on 8 cores. And it will just be the one way of doing parallel computing. And to be honest, it's as simple as Python once you get used to it. And I'm just going to leave it there. Thank you very much indeed.